Hey everyone, I'm Jason. This semester I've been working on APPLD-Lite, which is very fast adaptive planner parameter selection from demonstration. I've been working with Preston, who's a student not in this class, in independent study, Garrett Warnell with Army Research Labs, and Xiao, who's a postdoc here. So before I talk about APPLD-Lite, I should give a brief overview of APPLD, which is the work that this is based on. So last year, Xuesu, Garrett, and some other people came up with this paper, APPLD, which is Adaptive Planner Parameter Learning from Demonstration. The idea is, say you have a robot that navigates using a traditional navigation stack like raw smooth base, like the Jackal here, and you want it to be able to navigate in new environments effectively without, smoothly, without crashing into any obstacles. If you want to do this, then you usually have to hand tune a set of parameters for that navigation stack that allow it to navigate effectively in new environments. This requires, expert level robotics understanding, and it's very time consuming. So if you want a fully autonomous, end-to-end system, then you can use this method that they've come up with, by which you can provide a human demonstration driving around your environment. You can segment that demonstration into different environments, for each of which you would use a different set of parameters in order to navigate optimally or close to optimally. And in order to learn each of those parameter sets, you use basic behavior cloning with a black box optimizer. So this method works really well. It can navigate really effectively in new environments. But one major downside here is that it just takes way too long to train with the black box optimizer. Depending on your setup, what kind of environment this is running in, it usually takes longer than 8 hours. So this is not very useful in real-world settings in which maybe you just want to, take a demonstration, learn from that, and learn some suitable set of parameters from that in like 10 to 15 minutes, and then immediately thereafter have your robot navigate effectively in new environments. So to fix this, we introduced APPLD-Lite. We're trying to drastically reduce the amount of time that this sort of technique takes. So we're replacing the black box optimizer with parameter selection from a pre-existing library that we've assembled, each of those parameter sets has previously been demonstrated to be close to optimal in specific environments. So sort of roadmap for this project, how this technique works is we provide a demonstration, we generate a data set for a classifier based on that demonstration, and when you at deployment, you can query the classifier with the LiDAR data that the robot receives, and you can use that outputted prediction to dynamically reconfigure the parameters that the robot uses to navigate, so that it can navigate more optimally. So the status of this project, it is able to train and deploy in about 10 to 20 minutes, depending on the particular configuration, which neural network architecture you're using, or how you augment the data set and whatnot. This is better than the default parameter DWA as implemented, which is a local planning algorithm as implemented on Ross's move base. It's not yet on par with the original APPLD algorithm in terms of consistent time to completion through the maze in a smooth manner. So our final task here is basically to improve the classifier's robustness to noise. This seems to have been the main issue that we've been dealing with, and we've been trying out a number of different techniques to try to fix this, various neural network architectures and augmentations to the data set and whatnot. And we'll talk about that soon. So some additional backgrounds here. We've split this main task into two main subtasks. One is perception, which is basically asking the question, given this LiDAR data that we perceive in the environment, how can we extract meaningful structure and information out of that, so that we can learn the environment that we're in and distinguish it from other environments. And then there's this adaptive control, which is the problem of trying to adjust the parameters dynamically, where the parameters are kind of uncertain. And so on the perception side, some of the work that's kind of inspired us there's been a lot of work with deep learning for 3D LiDAR scene understanding, with especially with full-size autonomous vehicles. It's not so popular to do one or two-dimensional LiDAR deep learning stuff in the literature, which is what we're doing. And on the clustering side, there's a number of very successful clustering-based approaches. And then on the adaptive control side, there's this Apple paradigm, all these Apple papers, and these sort of idea of this cycle of learning. The main difference here is that instead of learning the parameters directly, we're learning to select pre-existing parameters from a library. Okay, so a bit of information about our approach here. So as I said before, the first step is to provide a demonstration driving through the environment. You can collect some data from this demonstration and use that to generate a data set which you give to your neural network. And we generate that data set using this algorithm. And this is basically trying to create a, all of your labels for the network are the LiDAR that you perceive, and then at each time step through the demonstration, and then the associated, or sorry, those are the inputs. The associated labels are the indices corresponding to the parameter sets that that allow the jackal to drive most similarly to how it did in the demonstration. And then one interesting detail here is that you can sort of generate these plans parallelized in Docker containers, and you can also do some other things to speed this up. That is to say that this part of the process, the amount of time this takes is basically negligible. So that's nice. And some details on our classifier. Yes, so right now, what seems to have been working the best is just a simple feed-forward network. One major issue here is that it seems not to be robust enough to noise in the LiDAR data, meaning that you can achieve very high accuracy on your training and validation sets, even regularizing training with early stopping, and you deploy it in the exact same environment in which you took the demonstration. And because there's so much noise in the LiDAR data, you can sometimes get predictions which are wildly different than what you expect. So that's something we're currently trying to sort out. And as I said before, we can reconfigure the parameters dynamically by queuing up a number of predictions and taking the mode of those predictions and setting the parameter set to that output of prediction. That keeps the updates to twice a second, which prevents any possibility of instability from changing the parameters too often. Okay, so we ran some updated experiments. We tested against human demonstration driving around the environment, and we also tested against default parameter DWA as implemented in Rothy's Moonbase. We took the mean of 3 successful trials, and then we tested APPLD-Lite. So as you can see, the results are not too different. They're pretty similar from the results earlier in the semester. We're still having issues with this navigation stalling. So in particular, so default parameter Moonbase would very, very frequently get stuck as it was trying to navigate around. And this is sort of a testament to the fact that those parameters are not very good for specific types of environments. So it would kind of stall, and you would have to help it. This would happen sometimes with APPLD-Lite with reduced frequency. It seems to be much less frequent now, but it still does happen. So where it would sort of predict a parameter set, that caused it to have a greater inflation radius, which means that it wants to stay a certain distance away from the obstacles. So it can kind of cause the plan to abort. So we're trying to, so in short, we haven't tested against the original APPLD method, but usually APPLD is able to basically match the human demonstration performance maybe usually exceed it by a few seconds faster. So in this case, these human demonstration takes were taken, driving the robot, like kind of accelerating it as it drove through. So this is sort of a rough marker for where we should be in this type of environment. And then some summary of what we've done here, and also an overview of the future work. So we've succeeded in this original goal of reducing the amount of time this type of system takes, and we're still trying to achieve performance which is comparable to the original APPLD method. We are faster than this default method though. And our current goal is we've basically been trying a number of techniques, different neural network architectures, training methods, different ways of augmenting our data set to try to make this more robust and have it generalize better, because there's so much noise in that LiDAR data. So we've tested out in RNN with the hope that maybe there was some underlying, like a temporal relationship between the data that could be exploited, and it seemed to have yielded worse performance. One downside is that it's also difficult to perform any sort of augmentation of the data set with an RNN, because it's the data has to be trained in sequence, so you can't do any it's hard to do any radical class rebalancing and whatnot. You can't just tack the data onto the end of your training set. And we've also tried some data set augmentation stuff. So we've been doing some geometric transforms, rotating the input data by plus or minus 10 degrees to try to keep it invariant to rotation. Trying to learn a mirror image of the course, and also rebalancing the training data. From the demonstration, usually there can be a very heavy class imbalance. Sometimes one or two classes will dominate maybe 60% of the predictions, so you have to rebalance the training data if you want the model to not just converge on one or two predictions for all inputs. We've also been doing some regularization. Both of these seem to have yielded some improvements. It's difficult to see it manifested in the results, but it seems to anecdotally it seems to be a lot better. And we've tested out a one-dimensional convolutional network, trying to learn trying to learn the underlying structure of the data better. This seems to yield little or no improvement, and it also takes longer to train. And some techniques we're interested in testing out. We're looking at an image-based two-dimensional CNN technique, since those seem to be so powerful. We're thinking of trying to project the LiDAR data onto a two-dimensional Euclidean space and treating it as an image, coloring it with the intensity. And so we have yet to test that out. And then there's a clustering-based technique that we're looking at that's proven to be effective in similar contexts, which we have yet to test. So the idea here is ultimately, once this is fully refined, we'll have on-site autonomous navigation that's fast, practical, collision-free, and is able to generalize to new domains. Thank you very much.
Cool. Questions?
Yeah, so the parameters that APPLD-Lite uses for the different contexts, are those the ones that learn from APPLD itself, or is it some other situation that those parameters come from?
The parameters that APPLD-Lite uses are the 4 that are in APPLD that they found. Those 4 parameter sets plus the 6 in APPLI.
So is that more context to classify in, or is it still those 4 that APPLD had?
Those are like 10 different contexts.
Oh, yeah, okay.
It's like curvy environments, wide open environment, obstacle filled, narrow corridor, and then 6 in APPLI where they found could be helped by optimization.
Okay.
In one form or another. Yeah.
So you said the LiDAR data was very noisy and that was causing issues. Did you consider doing any kind of pre-processing or smoothing to the data before you actually fed it into the network?
So one thing that we did was usually you get a lot of infinite distances in the LiDAR data, just because it sees way off to the side, and we did smooth that out. It's difficult to say how much that helps, but it's also difficult to, we could try, we considered normalizing the inputs, but one issue is that I think that the absolute distance from the LiDAR data is important and not just the relative normalized distances. So we could try that also. We'll see, you know, if that helps, but yeah, it could be good.
One more.
So if I understood correctly, the primary metric you used to measure like how well the APPLD-Lite worked was the time it took, right, to complete the course.
Right.
I was wondering, like, what if you were to consider like a different metric, like average distance maintained from like obstacles? Like, would that like necessarily help you like understand more about which like APPLD-Lite version works better?
I think that the default navigation stack usually, like it automatically tries to keep a certain distance from the obstacles, so you're kind of guaranteed in that regard. So that, I think, is the reason why we were so focused on, hyper-focused on speed as the primary metric of success here. So.
All right, let's thank our speaker again.